A rack railway is a steep-grade railway with a toothed rack rail, usually between the running rails. The trains are fitted with one or more cogwheels or pinions that mesh with this rack rail. This allows the trains to operate on steep grades above around 7 to 10%, which is the maximum for friction-based rail. Most rack railways are mountain railways, although a few are transit railways or tramways built to overcome a steep gradient in an urban environment. The first cog railway was the Middleton Railway between Middleton and Leeds in West Yorkshire, England, UK, where the first commercially successful steam locomotive, Salamanca, ran in 1812. This used a rack and pinion system designed and patented in 1811 by John Blenkinsop. The first mountain cog railway was the Mount Washington Cog Railway in the U.S. state of New Hampshire, which carried its first fare-paying passengers in 1868. The track was completed to reach the summit of Mount Washington in 1869. The first mountain rack railway in continental Europe was the Wittnau-Riegli-Bahn on Mount Riegli in Switzerland, which opened in 1871. Both lines are still running. Rack systems. A number of different rack systems have been developed. Today, the majority of rack railways use the ARB system. John Blenkinsop thought that the friction would be too low of metal wheels on metal rails, so he built his locomotives for the Middleton Railway in 1812 with a 20-tooth, 3 feet diameter cogwheel on the left side that engaged in rack teeth on the outer side of the rail. The metal fishbly edge rail with its side rack being cast all in one piece, in 3 feet lengths. Blenkinsop's system remained in use for 25 years on the Middleton Railway, but it became a curiosity because simple friction was found to be sufficient for railroads operating on level ground. Rack systems place the rack rail halfway between the running rails, with the exception of some early Morgan rack installations. The first successful rack railway in the U.S. was the Mount Washington Cog Railway, developed by Sylvester Marsh. Marsh was issued U.S. patent for the general idea of a rack railway in September 1861, and in January 1867 for a practical rack where the gear teeth take the form of rollers arranged like the rungs of a ladder between two L-shaped, wrought iron rails. The first public trial of the Marsh rack on Mount Washington was made on August 29, 1866, when only 1/4 of a mile of track had been completed. The Mount Washington Railway opened to the public on August 14, 1868. The pinion wheels on the locomotives have deep teeth that ensure that at least 2 teeth are engaged with the rack at all times. This measure helps reduce the possibility of the pinions riding up and out of the rack. Riggin. The Riggin rack system was invented by Nicolaus Riggin, working at about the same time as, but independently from Marsh. Riggin was granted a French patent in 1863 based on a working model which he used to interest potential Swiss backers. During this time, the Swiss consul to the United States visited Marsh's Mount Washington Cog Railway and reported back with enthusiasm to the Swiss government. Eager to boost tourism in Switzerland, the government commissioned Riggin to build a rack railway up Riegli Mountain. Following the construction of a prototype locomotive and test track in a quarry near Bern, the Wittnau-Riegli-Bahn opened on the 22nd of May 1871. The Riggin system is similar in design to the Marsh system. It uses a ladder rack formed of steel plates or channels connected by round or square rods at regular intervals. The Riggin system suffers from the problem that its fixed ladder rack is more complex and expensive to build than the other systems. Following the success of the Wittnau-Riegli-Bahn, Riggin established the Maschinenfabrik der International and Gesellschaft für Bergbahnen, a company that produced rack locomotives to his design. The Strub rack system was invented by Emil Strub in 1896. It uses a rolled flat-bottom rail with rack teeth machined into the head, approximately 100 mm apart. Safety jaws fitted to the locomotive engage with the underside of the head to prevent derailments and serve as a brake. Strub's U.S. patent, granted in 1898, also includes details of how the rack rail is integrated with the mechanism of a turnout. The best-known use of the Strub system is on the Jungfraubahn in Switzerland. It is the simplest rack system to maintain and has become increasingly popular. Morgan in 1900, E.C. Morgan of Chicago received a patent on a rack railway system that was mechanically similar to the Riggin back rack, but where the rack was also used as a third rail to power the electric locomotive. Morgan went on to develop heavier locomotives and with J. H. Morgan turnouts for this system. In 1904 he patented a simplified but compatible rack, where the teeth on the engine pinions engaged square holes punched in a bar-shaped center rail. J. H. Morgan patented several alternative turnout designs for use with this rack system. Curiously, Morgan recommended an off-center rack in order to allow clear passage for pedestrians and animals walking along the tracks. Some photos of early Morgan installations show this. A simplified rack mounting system could be used when the Morgan rack was not used for third rail power, and the Morgan rack offered interesting possibilities for street railways. The Morgan rack was good for grades of up to 16%. The Goodman Equipment Company began marketing the Morgan system to mining companies, and it saw widespread use, particularly where steep grades were encountered underground. By 1907, Goodman had offices in Cardiff, Wales to serve the British market. Between 1903 and 1909, the McKell Coal & Coke Company in Raleigh County, West Virginia, installed 35,000 feet of Morgan rack third rail track in its mines. Between 1905 and 1906, the Mammoth Vein Coal Company installed 8,200 feet of powered rack in two of its mines in Everest, Iowa, with a maximum grade of 16%. The Donahoe Coke Co. of Greenwall, Pennsylvania had 10,000 feet of Goodman rack in its mine in 1906. The Morgan systems saw limited use on one common carrier railroad in the United States, the Chicago Tunnel Company, a narrow-gauge freight carrier that had one steep grade in the line up to the surface disposal station on the Chicago lakefront. The ARBD system was devised by Roman ARBD, a Swiss locomotive engineer. ARBD worked for Riggin back at his works in Alton and later at his IGB rack locomotive company. In 1885, he founded his own civil engineering company. During the early 1880s, ARBD worked to devise an improved rack system that overcame the limitations of the Riggin back system. In particular, the Riggin back rack was expensive to manufacture and maintain, and the switches were complex. In 1882, ARBD designed a new rack using solid bars with vertical teeth machined into them. 2 or 3 of these bars are mounted centrally between the rails, with the teeth offset. The use of multiple bars with offset teeth ensures that the pinions on the locomotive driving wheels are constantly engaged with the rack. The ARBD system is cheaper to build than the Riggin back because it requires a lower weight of rack over a given length. However, the Riggin back system exhibits greater wear resistance than the ARBD. ARBD also developed a system for smoothing the transition from friction to rack traction, using a spring-mounted rack section to bring the pinion teeth gradually into engagement. The first use of the ARBD system was on the Harzbahn in Germany, which opened in 1885. The pinion wheels can be mounted on the same axle as the rail wheels, or driven shown separately. The steam locomotives on the Mount Lyell Mining and Railway Company had separate cylinders driving the pinion wheel, as do the X-class locomotives on the Nilgiri Mountain Railway. The steepest gradient on the rack section of Mount Lyell Mining and Railway Company was 1 in 15. The steepest gradient on the rack section of the Mount Morgan Railway was 1 in 16.5. Locker. The locker rack system, invented by Edward Locker, has gear teeth cut in the sides rather than the top of the rail, engaged by two cogwheels on the locomotive. This system allows use on steeper grades than the other systems, whose teeth could jump out of the rack. It is used on the Pilatus Railway. Locker set out to design a rack system that could be used on gradients as steep as 1 in 2. The rail.The system, the most common rack system in Switzerland at the time, was limited to a maximum gradient of 1 in 4. Locker showed that on steeper grade, the rail.The system was prone to the driving pinion overriding the rack, causing potentially catastrophic derailments, as predicted by Dr. Rail.The. To overcome this problem and allow a rack line up the steep sides of Mount Pilatus, Locker developed a rack system where the rack is a flat bar with symmetrical, horizontal teeth. Horizontal pinions engage the centrally mounted bar, both driving the locomotive and keeping it centered on the track. This system provides very stable attachment to the track, also protecting the car from toppling over even under the most severe crosswinds. Such gears are also capable of leading the car, so even flanges on running wheels are optional. The biggest shortcoming of the system is that the standard railway switch is not usable, and a transfer table or other complex device must be used where branching of the track is needed. Following tests, the Locker system was deployed on the Pilatus Railway, which opened in 1889. No other public railway uses the Locker system, although some European coal mines use a similar system on steeply graded underground lines. Lamella. The Lamella system was developed by the Von Roll Company after the rolled steel rails used in the Strub system became unavailable. It is formed from a single blade cut in a similar fashion to the rail.The system but typically wider than a single rail.The bar. The Lamella rack can be used by locomotives designed for use on the Riggin back or the Strub systems, so long as the safety jaws that were a feature of the original Strub system are not used. Some railways use rack from multiple systems, for example, the St. Gallen Gais Appenzell Railway in Switzerland has sections of Riggin back, Strub and Lamella rack. Most of the rack railways built from the late 20th century onwards have used the Lamella system. Rack and adhesion systems, pure rack systems. Rack and adhesion systems use the cog drive only on the steepest sections and elsewhere operate as a regular railway. Others, the steeper ones, are rack only. On the latter type, the locomotive's wheels are generally freewheeling and despite appearances do not contribute to driving the train. In this case the racks continue also in the horizontal parts, if any. The Fell Mountain Railway system is not strictly speaking a rack railway since there are no cogs with teeth. Rather, this system uses a smooth raised center rail between the two running rails on steep lines which is gripped on both sides to improve friction. Trains are propelled by wheels of braked by shoes pressed horizontally onto the center rail, as well as by means of the normal running wheels. Switches. Rack railway switches are as varied as rack railway technologies. For optional rack lines such as the Zentralbahn in Switzerland and the West Coast Wilderness Railway in Tasmania, it is convenient to only use switches on sections flat enough for adhesion. Other systems which rely on the rack for driving, such as the rail.Bahn in Zurich, STRBSK Kutpliso in Slovakia, and the Skanichplat rack railway, instead must switch the rack rail. The rail.Bahn switch works by bending all three rails, an operation that is performed every trip as the two trains pass in the middle. The geometry of the rack system has a large impact on the construction of turnouts. If the rack is elevated above the running rails, there is no need to interrupt the running rails to allow passage of the driving pinions of the engines. Straub explicitly documented this in his U.S. patent. Straub used a complex set of bell cranks and push rods linking the throw rod for the points to the two throw rods for the moving rack sections. One brake in the rack was required to select between the two routes, and a second brake was required where the rack rails crossed the running rails. Turnouts for the Morgan rack system were similar, with the rack elevated above the running rails. Most of the Morgan turnout patents included movable rack sections to avoid breaks in the rack, but because all Morgan locomotives had two linked drive pinions, there was no need for a continuous rack, so long as the breaks in the rack were shorter than the distance between the drive pinions on the locomotive. The rack rail could be interrupted wherever there was need to cross over a running rail. Turnouts are far more complex when the rack is at below the level of the running rails. Marsh's first rack patent shows such an arrangement, and the original Mount Washington Cog Railway he built had no turnouts. It was not until 1941 that a turnout was constructed on this line. There were more turnouts built for the line, but all were hand-operated. In 2003, a new automatic hydraulic turnout was developed and built at the base as a prototype. With the success of the new turnout, more new automatic hydraulic turnouts were built to replace the hand-operated ones. The new turnouts installed on the Mount Washington line in 2007 are essentially transfer tables. The locker rack also requires transfer tables. Cog locomotives. Originally, almost all cog railways were powered by steam locomotives. The steam locomotive needs to be extensively modified to work effectively in this environment. Unlike a diesel locomotive or electric locomotive, the steam locomotive only works when its power plant is fairly level. The locomotive boiler requires water to cover the boiler tubes and firebox sheets at all times, particularly the crown sheet, the metal top of the firebox. If this is not covered with water, the heat of the fire will soften it enough to give way under the boiler pressure, leading to a catastrophic failure. On rack systems with extreme gradients, the boiler, cab and general superstructure of the locomotive are tilted forward relative to the wheels so that they are more or less horizontal when on the steeply graded track. These locomotives often cannot function on level track, and so the entire line, including maintenance shops, must be laid on a gradient. This is one of the reasons why rack railways were among the first to be electrified, and most of today's rack railways are electrically powered. In some cases, the vertical boiler can be used that is less sensitive for the track gradient. On a rack-only railroad, locomotives are always downward of the passenger cars for safety reasons. The locomotive is fitted with powerful brakes, often including hooks or clamps that grip the rack rail solidly. Some locomotives are fitted with automatic brakes that apply if the speed gets too high, preventing runaways. Often there is no coupler between locomotive and train, since gravity will always push the passenger car down against the locomotive. Electrically powered vehicles often have electromagnetic track brakes as well. The maximum speed of trains operating on a cog railway is very low, generally from 9 to 25 km per hour depending on gradient and propulsion method. Because the sky tube has gentler gradients than typical, its speeds are higher than typical. List of cog and rack railways. Angola Lengorge, Ombenguela Railway 1906. Argentina Transandine Railway between Mendoza and Santa Rosa de los Andes, Chile. See Chile below. Australia West Coast Wilderness Railway in Tasmania, originally opened in 1896 to service the Mount Lyell copper mine and closed and completely removed in 1960s, rebuilt and reopened for tourists in 2003. Uses the arbed rack system. 1067 mm gauge. Mount Morgan Rack Railway on Mount Morgan. Rack system existed until 1952 when the line was deviated. Uses the arbed rack system. 1067 mm gauge. Along Colliery. Underground Lamella rack installed in 1984. Skytube Alpine Railway. Lamella rack in the Snowy Mountains. Opened in 1987. 1435 mm gauge. Blue Mountains Sewerage Project. Temporary 610 mm gauge construction railway, 1995. Austria Ackinsee Railway, Tyrol 1000 mm. Erzberg Railway, Styria. Geisberg Railway, Geisberg. Kahlenberg Railway, Kahlenberg. Doboling, Vienna. Schaberg Railway, Upper Austria 1000 mm. Schneeberg Railway, Lower Austria. Bolivia Rio Muletos Potosi Line. Brazil Corcovado Rack Railway, the Estrada de Ferro Santos Jundiaí, which became part of Red Ferroviaria Federal Sociedad Anónima 1957–1997, now owned by Mrs. Logistica. 1600 mm gauge between Paranapiacaba and rails.The. Teresópolis and Petropolis railways, both out of service, near Rio de Janeiro. More on German page. Chile Arica La Paz Railway, Arica La Paz. Santa Lucia Hill Tramway, Santiago. The Transandine Railway, Santa Rosa de los Andes, Mendoza, Argentina. The rebuild will be adhesion-only and user-based tunnel. Czech Republic Cog Railway Tanvald Harrachov. France Lyon Metro Line C Mont-Blanc Tramway. Montenvers Railway. Petit Train de la Rhône. Panoramique des Domes. Germany Drachenfels Railway. Harz Railway Rubland Railway. Holland Alban. Murg Valley Railway. Oberweisbach Mountain Railway. Schwarzer Valley Railway. Stuttgart Rack Railway, Stuttgart. Wendelstein Railway. Bavarian Zugspitze Railway. Greece Diakovtuk Lavita Railway. Hungary Fogas Kerekuvasat in Budapest. Hungary is a kind of cogwheel tram in the hilly Buda part of the city. Indonesia The Padang Sawalanto Line in West Sumatra. A railway in ACEH, no longer in operation but will be reconstructed. Ambarawa Railway Museum, still in operation as a tourist line using steam locomotives. Indian Nilgiri Mountain Railway, in the Indian state of Tamil Nadu, is also a World Heritage Site. Runs twice a day using steam-powered X-class locomotives built by the Swiss Locomotive and Machine Works. Italy Mont Cenis Pass Railway, temporary while main tunnel built. Vesuvius Funicular. Opacina Tramway. Ritnobahn. Superga Rack Railway. Principe Panorala Rack Railway in the city of Genoa. Estelero. Saltino. Lagonegro Castro Villaris Pesano Albanese of Ferrovi Calabro Lucan. Vibo Valentia Melito of Ferrovi Calabro Lucan. Rocket Asiago. Catanzaro Città. Catanzaro Sala of Ferrovi della Calabria. Parola Cosenza of Ferrovi dello Stato. Saline Volterra of Ferrovi dello Stato. Ditino Leonforte of Ferrovi dello Stato. Ditino Piazza Armerina of Ferrovi dello Stato. La Carabassa Filaga Palazzo Adriano Migazzalo of Ferrovi dello Stato. Agrigento Naro Licata, Japan Ikawa Line Ogawa Railway, US Uipass was the first rack and pinion line in Japan, on the Shin-Etsu line of the then Japanese National Railway. It was replaced in 1963 by a new parallel adhesion line, and in turn replaced by the Nagano Shinkansen line opened for the 1998 Winter Olympics at Nagano. Lebanon. A rack railway used to exist on the climb from Beirut to Syria. Gauge 1050 mm. Mexico. The 762 mm gauge Mapimi Railroad in Durango State had a short arbed rack section from El Cambio to Ohuela. The maximum grade was 13.6% and it was worked by two Baldwin 062T steam locomotives built in 1896 and two Baldwin 262T steam locomotives built in 1898 and 1900. The railroad closed in the early 1930s. Panama. Large ships are guided through the Panama Canal locks by electric locomotives known as mulas, running on rack rails on the lock walls. The new locks, projected to open in 2015, will use tugs. Portugal. There was previously a cog railway from Funchal to Monte in Madeira Island, which operated between 1893 and 1943, and went further up to Terreiro da Luta at 867 meters above sea level. Slovakia. Strbsk Acute Pliso Striper Rack Railway, Brezno, Tisovec Rack Railway, South Africa. There used to be a Riggin bag rack railway built by the NZASM between Waterville Boven and Waterville Onda. It was in operation until 1908. 3 feet 6 in gauge. Spain. Montserrat Rack Railway, the Valde-Anuria Rack Railway. Switzerland. Appenzell Bahnen, Bergbahn Rheineck Walsenhausen, Berner Oberlandbahn, also owning Skenigeplatte Railway. Schumada Fergal Lesen, Schumada Fergal Ollen Munthy Champere, Schumada Furbex Villas Brete, Schumada Furbline Lespi Acute Iades, Breens Rothorn Bahn, Schumada Furda Martin Chatellard, Schumada Fur Montroglian Rochers Dunai, Dampfbahn Furkerberg Strecker, Doldebahn, Gornegradbahn, Jovidzanradbahn, Jungfraubahn. The highest rack railway in Europe. Matterhorn Gotthard Railway, Monte Generoso Railway, Pilatus Railway, Regibahnen, Rorschach-Heidenbahn, Rorschach to Heiden, Vengenalpbahn. The longest continuous rack railway in the world. Zentralbahn, United Kingdom. Snowdon Mountain Railway, United States. The Chicago Tunnel Company used the Morgan rack system on the steep grade up to Grant Park. Manitou and Pikes Peak Railway, Manitou Springs, Colorado. Swiss-made diesel pneumatic rail cars, 1 or 2 car trains. Arbed rack system, Mount Washington Cog Railway, Bretton Woods, New Hampshire. Biodiesel and AMP live steam cog train operations with marsh rack system, world's first to be used as a mountain railway. Quincy and Torch Lake Cog Railway, Cog Rail Tram opened in 1997. Hancock, Michigan. Green Mountain Cog Railway, Vietnam. The Ta Lat Thap Cham line in southern Vietnam, abandoned after the Vietnam War, although a 7 km section remains in use as a tourist attraction. Built in the 1920s, the 84 km line had a cogwheel part 34 km long, running through 4 tunnels with a total length of almost 1,000 meters, taking trains from the Krongfa Pass up the Goan Musi Pass to Dalat. Rack railways in fiction. The Col de Fel Railway is a fictional cog railway on the island of Sodor in the railway series by Rev. W. Awdry. Its operation, locomotives and history are at least in part based on the Snowdon Mountain Railway. It is featured in the book Mountain Engines.